All right, hello everyone. So I'm Sarah Millholland. I'm an assistant professor at MIT, and I'm really excited to speak today about chapter 24 on the architectures of compact multi-planet systems. This was a chapter written by Lauren Weiss, myself, Erik Petigura, Fred Adams, Konstantin Batygin, Tony Bloch, and Christoph Mordasini. So I think that one of the most sort of defining discoveries within the field of exoplanetary science thus far is really just the sheer diversity of the observed exoplanets. In this space of planet size versus orbital period, planets populate almost the entire detectable space, making it clear that the planet formation process is capable of producing just an enormous diversity of outcomes. There does seem to be a sort of preferred mode of formation, though, and that is these small planets, roughly between the size of Earth and Neptune, in orbits with periods ranging from days to months. These planets are incredibly common, and they're frequently found in tightly spaced multiple planet systems, which we call the compact multis. So for the sake of definitiveness, in our chapter, we defined compact multis to be multiple planet systems containing planets with radii between the sizes of 0.5 and 4 Earth radii, and with orbital periods in between a day and a year. An amazing discovery of the last few years is that, in contrast to the diversity of the exoplanet sample as a whole, these compact multis exhibit some striking degree of uniformity. So for instance, here is an example of a few compact multis. These systems display this very orderly structure with nearly uniform spacing in log period and a tendency for size uniformity with a slight size ordering. Here's the full collection of multi-planet systems with 4 or more planets discovered by NASA's Kepler mission. The purpose of our chapter was to review in detail the observations of these compact multi-planet systems and their implications for planet formation theory. So that's going to be the focus of today's talk. Before proceeding, though, I want to note that I'll often be using the terms super-Earth and sub-Neptunes to refer to these planets. These definitions are based on the observed radius distribution, which exhibits a clear bimodality. So planets between the sizes of about 1 Earth radii to 1.8 are what we call super-Earth. These are thought to be sort of scaled up rocky worlds, whereas planets between 1.8 and 4 Earth radii are what we call sub-Neptunes, and these are thought either to be sort of rocky worlds enshrouded by some hydrogen-helium atmospheres composing a few percent by mass, or potentially water worlds. Okay, so diving in now, I want to begin by sort of taking a step back to discuss the history of compact multi-observations. The earliest sign that short-period super-Earths and sub-Neptunes were very common came from radial velocity observations in the pre-Kepler era. So for instance, the high-accuracy radial velocity planet searcher, the HARPS survey, started to observe many of these super-Earths and sub-Neptunes. They found that a robust estimate of the frequency of these systems shows that more than 50% of solar-type stars harbor at least one planet with any mass and with period up to 100 days. And they also said that most of the super-Earths belong to multi-planetary systems. Not long after this, the system which is now the poster child of transiting compact multi-planet systems was discovered. So Kepler-11 contains 6 known planets. You can see this incredible collection of transit data on the right here. And I want to emphasize that it's now a pretty commonplace to observe data like this, but it's worth remembering just how transformative this was at the time to see this many planets so close to their star and with such incredible precision in the transit data. Kepler-11 was also one of the first systems for which the masses were measured using transit timing variations, which are sort of deviations in the planet's orbital periods triggered by gravitational perturbations between planets. Kepler-11 has this incredible architecture, which is prototypical of these compact multi-planet systems, which I'll discuss in more detail soon. So Kepler soon started to reveal an abundance of these compact multis. Lissauer et al. In 2011 cataloged the multiple transiting planet candidates from Kepler and studied their architectures. They were able to identify that, quoting here, the large number of candidate multiple transiting planet systems observed by Kepler show that nearly coplanar multi-planet systems are common in short period orbits around other stars. And the next Kepler architectures paper was Fabrici et al. In 2014. This is all systems with 3 or more planets known at the time, so clearly these were proving to be pretty common. The present day estimates of the occurrence rates of compact multis lie in the range of about 30 to 80%. So although these estimates agree about the ubiquity of these systems, they disagree sort of on the extent of that. And the difficulty is predominantly in the fact that there's this inherent degeneracy between the multiplicity of the system and the mutual inclinations between the planets, which affects the observable of how many planets are transiting. Nevertheless, there is evidence that the close-in super-Earths and sub-Neptunes are more common around smaller stars, as we can see in this plot of fraction of stars with planets versus stellar effective temperature. And it's also apparent that compact multis appear to be a little bit more common around metal-poor stars, as we can see in this blue curve, which is sort of a proxy of occurrence rate versus stellar metallicity. So I want to now review the orbital properties of compact multis in more detail. These close-in super-Earths and sub-Neptunes in general show an increasing occurrence rate with orbital period out to around 10 days, beyond which that kind of flattens and maybe slightly drops. The distribution of orbital period ratios between pairs of planets within the same system is concentrated at fairly small period ratios of around 1.5 to 2. This distribution is fairly smooth overall, being well fit by a log normal. And most planet pairs are not near resonances, although there are these slight overabundances just wide of resonant locations. So resonances are locations where the orbital period ratios are near a fraction of simple integers. We can see these slight overabundances wide of these resonances. If we look at the orbital spacing in units of mutual Hill radii, we can see that the orbits are pretty close to what we call dynamically packed. So the mutual Hill radius is a measure of the sort of characteristic length scale of gravitational interactions between planets. Planets need to be spaced by more than about 5 to 10 mutual Hill radii in order to be dynamically stable. So this characteristic spacing of around 20 mutual Hill radii indicates that many of these systems are kind of piled up near their stability limit. We can go to another level of complexity and examine the correlations between the period ratios of planets within the same system. So this plot in the middle shows the relationship between the period ratios of adjacent pairs of transiting planets from compact multis from the California Kepler survey. A clear correlation can be seen here and is statistically significant. So for comparison, on the right here, we can see the expectation of this distribution if the period ratios were drawn at random from the observed distribution and subjected to sort of detection criteria and a stability requirement. The randomized systems do not exhibit sort of the correlation, and if we do this for many random realizations of randomized systems, we can infer that in the real data, we do see that planets in the same system tend to have similar spacings. One interesting question is whether the spacing correlates with the sizes of the planets. So when we examine the mean period ratio versus the planet mass, the mean sort of planet mass calculated from mass-radius relationships, there does seem to be a slight correlation. In particular, the very smallest mass planets don't appear to frequently have large period ratios, even though they could and still be stable. So moving on to some other orbital features, let's discuss the eccentricities. So the compact multis as a whole have pretty low eccentricities, nearly circular orbits. These eccentricities are difficult to measure for individual systems, and so most constraints have been made at the population level. One approach to this is to exploit the planetary transit duration, which depends on the eccentricity along with the period, the stellar density, the argument of periaps, and the impact parameter. So the dependence on eccentricity and argument of periaps can be seen nicely in this figure here. So using a sample for which the stellar densities are well known and using careful methods for modeling this distribution of eccentricities, multiple studies found that the eccentricities are most often in the range of about 0.02 to 0.05. So in some sense, this isn't really that surprising because of the tight orbital spacings between the planets. However, Yi et al. In 2021 found that the eccentricities are even smaller than required by stability. So given the low eccentricities, it should come as no surprise that the mutual inclinations are also very small, sort of in line with our expectations based on dynamical equipartition. So just as the transit durations can help constrain the eccentricities, the transit duration ratios between pairs of planets can help constrain the mutual inclinations. So specifically, the ratio of the transit chord lengths between pairs of planets within the same system is sensitive to the mutual inclination. Fabricati et al. In 2014 modeled this distribution and found that the mutual inclination dispersion was most consistent with around 1 to 2 degrees. Some of the most recent and thorough constraints on both eccentricities and inclinations come from forward models from He et al., who sort of forward modeled the Kepler planet population using statistical descriptions, applied a sophisticated Kepler detection pipeline sort of simulation, and fitted to various summary distributions. So they found evidence that the typical eccentricities and inclinations are negatively correlated with the multiplicity of the system, with systems with more planets having smaller eccentricities and inclinations. A final feature of the orbital architectures are the inner and outer edges. So it's important to note that the planets that we see are only the observed planets, and there may be additional ones, particularly more distant planets, that we haven't yet observed. However, we can sort of account for this by statistically modeling the selection biases, and we see that the inner edges appear to be consistent with expectations of the inner edges of protoplanetary disks, whereas the outer edges, on the other hand, appear to truncate at smaller orbital periods than expected from geometric and detection biases alone, suggesting that there is some sort of truncation or transition in the outer regions of these systems, that the compact multis are sort of limited to the inner parts of these systems. So to summarize what we've discussed so far, the orbits of these compact multis are incredibly structured and regular. They are dynamically cool, they're regularly spaced, and they have no strong preference for resonances. Incredibly, the structure and regularity of these orbital properties are mirrored in the physical properties of the planets. So first, planets in the same system tend to have similar radii as their neighbors. This was hinted in early studies by Lissauer et al., but was pointed out in detail by Weiss et al. In 2018 in this study of multi-planet systems from the California Kepler survey. So you can sort of see this by eye in this figure. If you scan your eyes down through the various systems, you can see that planets have radii that are more similar to those of their neighbors than you would expect if the planets were just drawn randomly from planets across the population. We can see this in another way if we plot the relationship between the radii of adjacent transiting planets. So this plot accounts for the difficulty of detecting planets in that planet pairs are only included if they pass sort of a swap test in which the planets would both be detected if they swapped positions. So we can see a high degree of correlation. In contrast, this plot in the middle shows the expectation based on planet radii that are drawn at random and that survive sort of a mock Kepler detection criterion. So you can clearly see a lack of correlation in that randomized sample. By doing this for many random realizations, we can conclude that planets in the same system tend to have similar sizes. The inter-system uniformity extends to masses as well. So in these plots, all planets in the same system have the same color and are connected by lines. We can see that systems tend to cluster on the mass-radius plane. And if we measure the dispersion of planets on this mass-radius plane for these observed systems, they're a lot less dispersed than they would be if the systems were assembled from planets drawn randomly from across the population. This is easiest to see if we compare the real systems on the left to a sort of random permutation of the systems in which the mass and radius pairs are shuffled. The little subplot in the bottom of this shows a measure of the dispersion on this mass radius plane for the real systems, the green line, relative to this distribution of random realizations. So this study, which by the way came after a preprint of the Weiss et al. Paper was released, considered planet masses from transit timing variations only. Intersystem uniformity of planet masses has since been explored by other authors, and they find that that mass uniformity is also present in systems with radial velocity measured masses. So this really fascinating tendency that planets have nearly uniform spacing and nearly uniform radii and masses is known collectively as the peas in a pod patterns. This was coined by Weiss et al., and the same effect is also referred to as intersystem uniformity. One question that you might have, or at least I had, was, well, we know that these close-in systems are composed of planets in two size classes, super-Earths and sub-Neptunes. So how can that be consistent with intersystem radius uniformity? So here on the right, we can see multi-planet systems with colors indicating whether the planet is considered to be super-Earth or sub-Neptune. Many systems have planets with both types. And so here is a comparison of the radii of planets of adjacent pairs split by whether you're considering super-Earth pairs, sub-Neptune pairs, and so on. So in this study, we tested for intersystem radius uniformity within the separate categories of super-Earth and sub-Neptune, and found that intersystem radius uniformity is stronger than random expectation even when split up into these size categories. So in other words, two super-Earths in the same system are more similar than two super-Earths drawn from the population. One thing that's important to consider is the role of detection biases. So it's important to check whether these patterns of uniformity might have some contribution from selection biases. So this issue was raised by Zhu et al., as well as Merchikova and Tremaine. And there's a thorough discussion of this in Weiss and Petigura 2020, as well as in our chapter, so I won't sort of talk much about it here. But to me, I think one of the strongest pieces of evidence that this is not the effect of detection bias is that there are now these incredibly advanced forward models of the Kepler planet population, which include these very sophisticated simulations of the Kepler detection pipeline. And these results show that the models require similar sizes and spacing in order to match the Kepler data. Moreover, different groups with various independent methods and different data sets find evidence for this uniformity. Okay, so I've now reviewed the observations of compact multis and discussed their intersystem uniformity at length. I think the fundamental question that surfaces then is, what is it about planet formation that makes compact multis be like peas in a pod? And this tendency towards intersystem uniformity has to be tied to these specific sort of fundamental processes in planet formation. So this question was really at the heart of our chapter. I'm going to sort of spoil this slightly and say that I think we're still not sure about what the dominant drivers of the peas in the pod phenomenon are. There are several viable theories that have been proposed, and this is still a very active area of research. So fortunately, though, by trying to answer this question, we can learn more about the physics of planet formation. So I'm going to spend the rest of the talk now discussing these physical mechanisms. It's useful to consider the following schematic roadmap to organize this discussion. So the physical processes can be broadly split into three categories: the disk properties, planet disk effects, and planet-planet effects. So disk properties are set by the formation of the star disk system. Planet disk effects include the conglomeration of dust and rocky material into progressively larger bodies, accretion of gas onto the planet, and migration driven by planet disk interactions. And lastly, planet-planet effects include any sort of pairwise interactions, such as gravitational effects leading to sort of enhanced long-term stability. So these three stages cover the full planet formation process somewhat temporally. So I'll first turn our focus onto how the global properties of the star disk system influence the emergence of compact multis and set their characteristic mass scale. One factor influencing the types of planets that form and their mass is the solid mass budget. So based on the sort of physics of the collapse flow that produces stars and disks, one finds that the initial disk mass is in the range of around, very roughly in around 1 to 10% of the mass of the star. So this corresponds to an initial solid mass budget of around 30 to 300 Earth masses for solar metallicity. Given that compact multis typically contain multiple planets with a few Earth masses of material each, this implies that the metallicity must be greater than about 0.1 solar value in order to produce such typical systems. In addition to the total mass of solids in the disk, the radial distribution of those solids is also relevant for planet formation. So when disks are built from the infall collapse flow that produces their stellar hosts, the surface density distribution has a nearly power law form. Star formation theory predicts power law indices in the range of about 5/3 to 7/4, whereas ALMA observations suggest somewhat shallower profiles. The minimum mass solar nebula and minimum mass extrasolar nebula, which consider the observed planets in their current locations and sort of spread out the mass to construct a surface density profile, find indices in the range of 1.5. More specifically, the most recent effort at this by Dai et al. Finds a power law index in the range of 1.75. So it's helpful to note that a sort of purely peas in a pod configuration, which is equal masses in units of equal log semi-major axis spacing, has a power law index of 2. So importantly, this is a steeper surface density distribution than the disks that gave rise to it, which suggests that the material must move relative to the move inwards relative to the initial distribution to create the observed planets. So the formation of the star disk system sets the sort of global conditions in which planet formation occurs. Within this environment, dust and rocky material coalesce into larger bodies, generating protoplanets. And sort of the specific processes by which this growth occurs is a topic of a lot of research, which we heard a lot about in the wonderful talk by Michael Lambrix earlier today. So I'll be just glossing over a lot of this here. But so here I want to review these processes and consider the idea that this intersystem mass uniformity might be created at the birth of the planets. So in order to understand the emergence of these peas in a pod phenomenon, it's valuable to quantify the characteristic mass scales of the planet formation process. The building blocks of planet formation are the planetesimals, and it's widely thought that planetesimals are generated through the direct gravitational collapse by the streaming instability, which we heard about earlier this morning. Various analytic and numerical means have been used to estimate the sort of characteristic planetesimal mass. These approaches yield planetesimal radii on the order of about 1 to a few hundred kilometers, with the analytic estimate slightly overestimating the numerical results. Nonetheless, this suggests that the formation of the planetary building blocks themselves from the streaming instability might instill some degree of sort of mass uniformity onto the newly born planetesimals. These planetesimals can then continue their growth through sort of two distinct pathways, either pairwise collisions with other planetesimals or sort of accretion of small rocky bodies known as pebble accretion. So I'll focus on pairwise collisions first. Growth through collisions occurs as the planetary embryos interact with other bodies in their feeding zone. So this growth cannot persist indefinitely, and it stalls when the planetary mass reaches the isolation threshold, which relies on the fact that the planetesimal feeding zone available to a growing protoplanet can only extend over a few Hill spheres in either radial direction. So this figure shows the isolation mass as a function of orbital radius for a series of surface density profiles, normalized to the sort of the minimum mass solar nebula value of the solid surface density. An immediate result is that the isolation mass itself can be relatively uniform. However, the value of the isolation mass is on the order of the mass of Mars, and thus a lot smaller than the typical masses of super-Earths and sub-Neptunes. So this implies that there would have to be some sort of post-isolation phase of giant impacts to consolidate these embryos into bona fide super-Earths and sub-Neptunes. A different mode of planetary growth occurs through a regime called pebble accretion, in which a growing body captures millimeter to centimeter sized particles through gas drag-assisted gravitational capture. So if vertical settling of solids is efficient, such that pebbles form sort of a thin subdisk, accretion can proceed in the efficient 2D regime, and bodies can grow very rapidly. Pebble accretion is also driven by, is facilitated by the radial drift of solids, and so it can therefore access mass reservoirs from larger separations. However, if the solid component of the disk is vertically well mixed with the gas, then accretion proceeds in the 3D regime, which is much less efficient. And in the inner disk, 3D accretion is likely to be the dominant mode, so it's unlikely to drive significant planetary growth there. Regardless of the accretion mechanism, though, an important feature of pebble accretion is that it's self-limiting. In the vicinity of a sufficiently massive body, the planetary gravity locally accelerates the gas above the Keplerian velocity. So when this happens, the pebbles then circumvent the planet and sort of stop the growth. The pebble isolation mass has a cubic scaling on the disk's aspect ratio, h/r. And so this factor, h/r, can vary from disk to disk, meaning that pebble accretion could instill a sort of rough mass uniformity within an individual system, but different masses from system to system. Finally, an inescapable consequence of this planetary growth is the onset of disk-driven orbital migration, which usually tends to move bodies to smaller orbital radii. Although it's generally agreed that migration probably occurs for at least some subset of these super-Earths and sub-Neptunes, its degree of importance is still debated, which I'll discuss a little bit further in a few slides. Okay, so far we've considered the idea that this inter-system uniformity might be instilled at the sort of birth of the planets themselves due to these characteristic mass scales of planetary growth. However, as these planets grow, their mutual interactions can't be ignored and in fact dominate at sort of later stages of growth. So here I want to consider the idea that maybe this inter-system uniformity is created or at least influenced by planet-planet effects after the initial formation. Okay, so one of the theories of compact multi-formation holds that these planets might form at larger orbital distances and migrate inwards under the influence of disk-driven migration. However, in the process, the planets can get captured into these resonant convoys, resonant chains. But the observed planets are not predominantly resonant. So these resonance chains would need to be broken through instabilities and collisions, consolidating the planets into a fewer number. So several authors have investigated how this epoch of planet-planet collisions might affect inter-system uniformity. They find that planet-planet collisions do not destroy inter-system uniformity entirely and might, in fact, even help produce it. So for instance, Goldberg and Batygin considered this inter-system mass dispersion in this sort of breaking the resonance chains hypothesis. So starting out with a high degree of inter-system mass uniformity and allowing these collisions to occur, they found that the collisions do gradually increase the mass dispersion, but they result in a level of dispersion that's pretty well matched to the data. A recent paper by Lammers et al. Considered sort of the opposite question of what happens if you start out with bodies that are more mass diverse than the observations. And they found that the collision, so actually they're starting out with the mass dispersion sort of up here if we look comparison to the Goldberg and Batygin picture. And they find that these collisions actually tend to reduce the mass dispersion, making systems more uniform. So either way you look, whether you're starting with systems that are more or less uniform than the observed systems, the final systems tend to end up with the degree of mass uniformity that we see in the data. As for another role of planet-planet interactions, if we step back and think more generally, we can consider the energy sort of shared by growing planets. So Adams et al. Pointed out that that many of the observed properties of the peas in a pod phenomenon can be understood by considerations of energy optimization. So suppose that you have two planets growing subject to the constraints of fixed total mass, fixed separation, and fixed total angular momentum. One can then find the lowest energy state of that system. So this plot shows the result of that calculation where the different curves show different orbital spacing. And if we look for masses, if the total mass in the planet pair is less than around a few tens of Earth masses, then the energy optimized state is one in which the planets have nearly equal masses. However, if the total mass in the planet pair is beyond some threshold value, which depends on the planet-planet separation, then it becomes more energetically favorable for one planet to experience sort of runaway growth and take all the mass. Very interestingly, this effect is also seen in the observed planetary sample, that systems that contain giant planets do not exhibit the same peas in a pod behavior as systems with lower planet masses, which is very supportive of this theory that energy optimization might be an important factor regulating their growth. Okay, so the previous sections explored how this intersystem uniformity could potentially arise through processes of planet formation and planet-planet interactions that regulate mass growth. In the last few minutes, I just want to take a time to explore how all of these processes might work together in a comprehensive framework. So here we can ask the question of, can population synthesis models reproduce the basic features of peas in a pod? In brief, population synthesis models attempt to simulate the formation of an entire population of planets end-to-end by incorporating all possible physics in a self-contained way, and attempting to compare the resulting synthetic planetary systems to the data using sort of synthetic detection. Population synthesis is a very rich field in and of itself, and there have been way too many sort of developments for me to review them here. But the results that I'll be focusing on are those from the new generation planetary population synthesis, or the Generation 3 Bern model. The Bern model is a global model of planet formation and evolution based on the core accretion paradigm. So the range of included physical processes are given in this large figure here. So this top panel represents sort of the starting point of the model, where several protoplanetary embryos are embedded in a disk of gas and planetesimals. The second picture displays the processes that are included, and sort of including planetesimal accretion and gas accretion. And the final panel shows sort of additional physics that are incorporated in the model. The initial conditions for these models are varied in a Monte Carlo fashion, producing sort of synthetic populations, which then can be compared to the observations using simulated sort of detection pipelines. So here's a realization of the synthetic planet population in the space of planet radius versus orbital period. The larger and darker points are the sort of planets that are detected according to this synthetic detection, whereas the smaller, lighter dots indicate sort of the underlying distribution. The model recovers several of the broad features of the planet population, including this abundance of close and small planets, the radius valley, and they do produce some systems that are very similar to the uniform compact multis, such as this yellow system here, as well as some systems that are more size diverse, like this one. On the right here, we can see some synthetically generated systems with 5 or more planets. Many of the synthetic systems show these intersystem regularities like the observed systems. So to see this intersystem correlations more clearly, we can explore the relationships between the radii of adjacent planets in the same system. So the left plot, whoa, I don't know why that's so blurry. Sorry about that. Okay, but this plot shows the underlying distribution, and this one shows the radius relationships for the synthetically detected systems. So these findings show a correlation, which is in excellent agreement with the data. This is not a hard-coded result of this planet population synthesis model. Rather, the intersystem correlations are a natural consequence of the existence of these characteristic mass scales arising from these different sort of governing physical processes and the n-body interactions. So just very briefly then, how does this intersystem uniformity come into existence? This figure shows the formation pathways of these close-in multi-planet systems. The left panel shows the mass, the sort of formation tracks of initially 100 planetary embryos in planet mass and semi-major axis space, whereas the right panel shows those tracks in semi-major axis versus time. So they illustrate how planets migrate, capture into resonance, and undergo collisions. The innermost 6 planets produced here exhibit a strong degree of mass uniformity and obtain their final masses from a series of giant impacts. So thus it appears that in these population synthesis models, the final set of giant impacts drive the uniformity. However, it's still, I think we need further work to understand why these giant impacts themselves are tending to drive the systems towards this uniformity. I think this is a very ripe area for future exploration. So now that I'm out of time, I'm just going to keep this summary super brief and just say that it appears that planet formation creates a sort of preferred type of planetary systems, super-Earths and sub-Neptunes and compact multi-systems, which are dynamically cool, dynamically packed, and have this tendency towards uniform radii and masses and spacing. This intersystem uniformity likely arises from some combination of characteristic mass scales from planet formation, instability-driven sculpting, or energy optimization. But we still don't know the main driver. And I think that ultimately this will continue to work on this. It provides important clues for planet formation that require further work to fully appreciate. I also want to thank the Kavli Institute for Theoretical Physics. In the summer of 2021, a subset of our group who could make it joined up there to work on our chapter for a week, which was a really awesome experience. So I want to thank the KITP for their hospitality. With that, I'll thank you and take any questions.
Thanks, Sarah. So questions, let's start up in front.
Peter Wojtke, Graz, Austria. I may be wrong, but I had the impression from your graphs of the planetary systems that you have many systems where the sub-Neptunes are more on the outer side and the super-Earth are more on the inside. Now this community started with the old idea that you get the rocky planets inside of a snow line and the gas giants outside. Is there any statistical correlation that this might be actually related to snowline? Is this hypothesis now back?
Yeah, great question. Yeah, so in this plot, so these are the super-Earth pairs where we have 2 super-Earths. These are sub-Neptune, sub-Neptune. This is where you have a super-Earth interior to a sub-Neptune, and these ones are sub-Neptune interior to a super-Earth. So indeed, there are many more cases where you have a sub-Neptune exterior to a super-Earth than the other way around. I think probably the dominant cause for this might be atmospheric mass loss. So if many of these planets begin as sub-Neptunes, then the ones that are closer in could experience atmospheric mass loss from photoevaporation or core-powered mass loss. And that, I think, is probably what's sculpting this.
So did you try to correlate that to the snowline?
No, yeah. I mean, these are pretty close in still, so like you can see 30 days is right here. So I think, yeah, that might be an interesting thing to look at if we consider the idea that maybe these are migrating from further out. Thanks.
Okay, let's do front right.
Hi, Wei Zhu from Tsinghua University in Beijing. So on this piecing apart pattern, so I just want to make one comment. So I mean, this we do see these types of patterns in the system. But I guess the main question or the key question is whether or not this pattern is representative of the whole population, in particular the unseen population, right? In fact, if you look at our solar system, the most accessible planets by a transit mission, Venus and Earth, would have similar size and similar mass, but they are not representative of the total population. And I noticed you concentrate this talk on compact multis, which show more likely this piecing apart pattern. But I guess then the question is whether or not, how often do you have these compact multis? Now you quote this fraction to be 30 to 80%, which is, I believe, the total fraction of stars with this type, with planets that would be observable by Kepler, right? But the compact multis, namely if you have at least 3 or even more than 4 planets, that's a very small fraction of the total observed system, and presumably the underlying intrinsic fraction as well. So I think it might be useful to make the point that this pattern, it's real in the observed data, but they may not be representative of the total population.
Right, yeah, so all of these inferences have been made for these like close-in planets, so we don't really know what's happening beyond like 100 days, for instance. Like everything I'm saying is only pertaining to the close-in planets. Also, yeah, similarly, we don't know, like if we just see a single transiting planet, there's may be and probably are other planets in the system, but right now we don't have a way of assessing the intersystem correlations there, except maybe potentially radial velocity studies. But I think I like the work of Matthias, who's sitting right here, where they sort of construct a forward model that describes the entire Kepler population and it captures the single transiting systems only. And so if you consider the idea that the whole population is a sort of uniformly sort of statistic construction, then you can sort of make inferences that way.
Well, I do have some comments on that work, but we can discuss later.
Okay.
Okay, let's go up front here.
Oh, hi. This is Michael Poon, University of Toronto, Canada. My question is, if there exists a multi-compact system, but the mutual inclinations are non-zero or even like large, would it be possible to observe this at all, like through like a really good radial velocity or something like that?
Sorry.
Oh, over here.
Oh, you're over there. Sorry.
Yeah,
okay.
yeah.
Yeah, I mean, like, I think it would be really, really cool if we can get ultra high precise radial velocities and be able to not only get the masses of like these systems using radial velocity, but getting masses of systems that have non-transiting planets. Then we could really, really assess whether this intersystem mass uniformity is present in sort of the whole population. Right now, we can't really do much if we just see a single transiting planet.
Okay, cool, thanks.
Okay, let's go in the back left.
Hi. Yuji Matsumoto from Naoji, Japan. So thank you for nice review. In your observational part, so I think your review is based on the CKS data, and I know diet actually shows so CKS data and RV data have some different in factor or power index. So do you have any comment on such difference of orbital or physical properties in between the CKS data, CKS planet and RB planet, or CKS planets and test planets?
CKS and TESS?
CKS, CKS, RB, and TESS.
Okay, yeah, like mass uniformity using radial velocity?
Yeah, mass uniformity or any inclination, right. Eccentricity.
Yeah. So, I mean, the thing about Kepler that was so wonderful was that it observed for 4 years, so we got a really long baseline which we could get a homogeneous sample of planets out to fairly large periods. And we can't do that as well with TESS multis. But there have been studies that looked at intersystem mass uniformity using masses from radial velocities, which also find evidence for intersystem uniformity. And there they considered essentially all systems that have any mass measurements from radial velocity. So including Otegi et al. 2022 and Goyle and Wang 2022, I think.
Thank you.
Okay, let's go in the back in the middle.
Yeah, hi, I'm Bertram Bitsch, Max Planck Institute for Astronomy, Heidelberg. Thank you for the very nice talk. I wanted to say that in our Breaking the Chains model with pebble accretion, we of course also reproduce these piece in a pot style pattern, but we also focus on period ratios and the radius valley composition, which we, I think, match very, very well. So I was wondering if you could comment if that planet population synthesis that you showed in the end can also reproduce these patterns that you introduced at the beginning but did not talk about.
Right, yeah. So I do think I have a plot of, yeah, so okay, I do not have that plot, but I'm not an expert on the burn model group's work. I think, if I recall correctly, that they still produce a little bit too many resonance systems. Someone could correct me if I'm wrong, but so yeah, it is still a challenge of like, if we have migration into resonance, how can we reduce the number of those resonances to match the observed data? I think their broad feature is still pretty close to the observed period ratio distribution, but there might be a bit too many resonances.
Okay, thank you.
Yeah.
Okay, we have about 5 minutes left, so let's keep the question short. So let's go in the back right.
Huan Yutong from Tokyo Institute of Technology, Japan. And I have two questions. The first one, that is, could you please comment on the hidden and non-transiting co-Jupiters outside the piece in the pod, and which breaks the piece in the pod pattern? And the second one, that is, could you please comment on the Goyo and Wong 2020, which you have quoted just now, and which derives the Gini index, and says the mass in large difference can also be stable, and via radial velocity we have found some of these systems. Thanks.
Yeah. So on the first question, so again, so the things that we're inferring are just for short period planets. So we're saying that planets inside of 100 days or so have this uniformities. And of course, like if there's giant planets further out, the whole system does not adhere to this trend. I think a very interesting thing to see in the future would be whether the presence of giant giant planets affect any of those intersystem properties. And Matthias, he again has a very nice poster on this based on the recent results from the Lauren Weiss paper that just came out. So I think there's going to be really interesting things there. Second question on Goyal and Wang, yeah, they present a very nice metric for understanding, for kind of computing mass uniformity. I'm not sure, what more to comment on it right here, but I'd be happy to chat more about it if you'd be interested.
Thank you.
Yeah.
Okay, up front.
Hi, Max Goldberg from Caltech. To what extent did these different formation models predict, compositional uniformity, and is that a testable way to distinguish between them?
That's a great question. So in this, so I believe in the burn model, they include sort of here indicating like the core ice mass fraction, so sort of one proxy for composition. I would have to probably direct you to those papers to see in detail whether they predict compositional sort of uniformity, but I think if you consider that these planets are forming near each other, that might also be one prediction. I am not an expert. Yeah, be happy to look into those papers more, though.
Okay, we only have time for 3 more questions. We're going to do 1 in the front and then 2 in the back. So.
Hi, this is Eiichiro Kokubo from National Astronomical Observatory of Japan. Thank you for the very nice talk. So I'm interested in the relation between piece in a pod pattern and multiplicity.
Mm-hmm.
So did you see if the degree of piece in a pod pattern depend on the multiplicity number of planets?
So when we do inferences of like the whole population, we are looking, so like for instance, like plots like this on the left considers all multiplicities like 2, 3, 4, and so on. And Lauren, I don't know if you have comment on whether the strength of uniformity depends on multiplicity at all. Do you have any?
I think that's an area that's ripe for exploration. Our chapter does explore in particular some patterns in the higher multiplicity systems with 4 or more transiting planets. There's about 50 such systems thanks to the Kepler mission. It would be great to get more.
Thank you.
Yeah, thanks.
Okay, back left.
I'm Kenji Kurosaki from Kobe University. I'm very interested in the non-uniform systems. Well, if giant impact occurs, most of the atmosphere should be easy to escape. But on the other hand, by definition, giant impact needs a large eccentricity. So my question is, does the non-uniform system also has an eccentricity, large eccentricity or very low eccentricity?
Oh yeah, that's a great question. So I think if there's a sort of final large giant impact, that might drive some more size diversity, and I think you're right that it would then also drive an eccentricity. The thing about eccentricities is that they can often be then tidally circularized over time, so it's a little bit hard to see the sort of giga-years-old systems and compare. That's a great question. I think I need to think more deeply about it.
All right, thank you very much.
Okay, we have time for one last question in the back.
Hey, hi Sarah, this is Johanna Tusky from Carnegie EPL. A wonderful talk, thank you. If you go back to the plot, we were looking at super-Earth, sub-Neptune, those pairs. I just was wondering if you found closer inter-system density, like that the densities are also closer together than a random population. I don't know if you have a large enough sample of densities to do that.
Yeah, so unfortunately this study was just radii, so we didn't have masses. I think once as the sample grows, looking at inter-system density variations would be very, very interesting.
Okay, thanks.
Thanks.
Okay, let's thank Sarah again.